Hi everyone, welcome on the next MedChem Essentials seminar. Today we'll be talking about volume of distribution. This is part of the second large block of our series related to half-life. Today we'll be talking first about body compartments, then about different compartmental models, finally and about blood flow, and then we will move into description of the concept of volume of distribution and some practical example illustrating the concept of volume of distribution. When we are talking about body and how the drug, the concentration of the drug changes over time, it's kind of impossible to treat the body literally as it is because it is just too complex. So we are simplifying body into some models in order to describe the behavior, the changes of the concentration of the drug. So one of the first model is so-called one-compartment model. In the one-compartment model, we are simplifying the whole body into one reservoir. After intravenous administration, the drug gets distributed in the body, and then after administration, which happens at time point 0, we see linear drop of the concentration with time. So this model can be applied in situations where actually we see this linear drop of concentration of the drug through time. So this happens when the drugs get distributed very rapidly throughout the body, and also for drugs that do not distribute throughout the whole body and they stay within the plasma. The second model is a two-compartment model. Here we have a central and peripheral compartments. Immediately after administration, the drug gets distributed into highly perfused organs. Of course, it will be present in plasma, but also in highly perfused organs like kidneys, lungs, liver, and heart, and also brain. After some time, the drug is being administered and distributed into peripheral system, peripheral organs with low perfusion, like muscles, fat tissue, and other organs. If we were to plot the changes of the concentration of the drug through time, we see two different kinetics. Up to the 2-hour time point, we have a logarithmic changes, logarithmic plot describing the changes of the concentration. This is the so-called distribution phase. So after distribution, after administration of the drug at time point 0, for 2 hours, the drug is being distributed to peripheral tissues. And after 2 hours, it is already distributed. And here we begin to see a linear correlation, linear drop of the concentration of the drug through time. So simplifying the things, like describing in this more detail, we can say that organs with a similar blood flow and perfusion rate, they form a single compartment. So how we described this before, organs with a high perfusion rate, the highest is lungs, next are kidneys, liver, heart, brain, you see thyroid glands, adrenal glands. Those organs, they will they will contribute to the central compartment. Whereas the low perfusion organs like bone, adipose tissue, muscles, skin, this is the peripheral compartment, and here the distribution into those organs will take some time. Now let's move to the core concept of volume of distribution. So we have a reservoir. This is our body. Now let's say we are operating within the one compartment model. This is the reservoir, and extractor are the organs that remove the drug from the body, like liver and kidneys. So when we are administering the drug into the reservoir, we are administering a certain amount of the drug that will be present within a certain volume of the reservoir. So the concentration is the amount divided by the volume. And after the distribution is complete, the concentration of the drug in plasma will be a function of the dose and the extent of distribution into tissues. So the more of the drug gets distributed into peripheral tissues, the lower will be the concentration of the drug in plasma. So volume of distribution is the amount of drug in relation to the plasma drug concentration. And by that definition, we will say that is the amount of the drug in the body divided by the plasma drug concentration. And here we have a simple example that will illustrate this concept. So very simplifying, we have a 1 liter volume of reservoir. And into this reservoir, we are adding an activated charcoal, 10 grams of it. This will be these 10 grams of activated charcoal. This will be our peripheral tissues. And then to the reservoir, we are adding 100 milligrams of a drug. After stirring for a little while, 99% of the drug will be absorbed into charcoal, which means that the final concentration after distribution is complete will be equal to 1 milligram per 1 liter. So the volume of distribution in this case will be 100 milligrams divided by 1, which is 100 liters. As you can see, this is 100 times greater than the actual volume of the system. So the volume of distribution is directly related to how much of the drug is being distributed, removed from the plasma and stored within peripheral tissues. And it very rarely corresponds to physical volume. As we will see later in the future, this almost never, very rarely reflects the actual volume, physiological volumes like plasma volume 3 liters, extracellular water 16 liters, or total body water of 42 liters. That's it for today. Thank you very much. See you next time.